thing, if you listened to Bart's talk today, that he said repeatedly, is that symmetric encryption schemes do not give you authenticity, or confidentiality does not equate authenticity. Namely, the encryption and decryption mechanisms are made in such ways so that when an active adversary modifies in some way the data that is transmitted over a channel, that cannot be spotted by the decrypting party. And for that purpose, we want a different algorithm, a different scheme that would ensure that any such intervention will be visible to the recipient, as well as encryption will hold. For the authentication purposes, we use in symmetric cryptography traditionally message authentication codes. So, as I said, traditionally we also have separate development of encryption schemes and message authentication codes. But it was only, I would say, not so recently anymore, in the last 15 years that people realized, or 20 years, people realized that these goals go together for most of the purposes we need to realize with these primitives. And that's why we have authenticated encryption. What does the authenticated encryption do? That again, we have two parties sharing a secret key, and one party wants to communicate to another party. It encrypts some message into a ciphertext C, and that ciphertext is also authenticated in the sense that any adversarial party would not be able to modify C and T in such a way that Bob doesn't notice that this happened. And also the confidentiality property would ensure that the adversarial party doesn't learn the message underlying the ciphertext M. And these two goals of authenticated encryption, as we started the talk with, are called confidentiality and authenticity. Somewhat informally, I would say that confidentiality means that the ciphertext is indistinguishable from random, and authenticity means that we have ciphertext integrity. Namely, this is a unique pair, T belongs uniquely to that ciphertext C. However, when I talk about authenticated encryption nowadays, in most of the cases we refer to what we call Nonce-based authenticated encryption. There is one additional input here that comes to the authenticated encryption algorithm, and that is the nonce. And for the moment, I would say that the nonce we just require to be a unique value that doesn't repeat on its application. There is one additional piece of data called associated data, and this is the A symbol here. So this is like a piece of data that is different than the message data, because for the message we would ensure both confidentiality and authenticity, but for this piece of associated data we might only need to ensure only authenticity. So that may be some header information that we don't need to hide, but just need to authenticate that it is correct. So this is normally how an authenticated encryption scheme looks nowadays. It integrates basically the encryption and authentication mechanism into one building block, or into one scheme. AE, or authenticated encryption, is important and it's very relevant in almost all applications of symmetric cryptography. We need, where we think of encryption, we would need most probably authenticated encryption. And so any data that travels over wire on unwired channels, so that needs to be both authenticated and encrypted, because, as I said, there are risks of modifications of the ciphertext. So then you add authentication, and thus authenticated encryption. Not only data in communication, but data at rest requires the same provisions. And there we have storage, disk authenticated encryption, and so forth. These are not the only applications. There are very many novel applications, which I call emerging applications, and particularly in the domain of IoT. There are billions of devices that still don't have deployed authenticated encryption mechanisms, but would need that deployment. And we can think of sensor networks, automotive industry, 5G, industrial control centers, and these all, any wearable technology, these all would require that the data that travels through the network is ensured to be both confidential and authentic. Another application that is a very novel application, or because nowadays data in computation is gaining more traction, and as Nigel will talk about that topic, we also use, not surprisingly, authenticated encryption there, and we have to see how that fits into that domain, and this is a very novel topic of research. The CISR competition indicates how important authenticated encryption as a topic and as a what's the practical relevance of authenticated encryption. It was a competition that ended in 2019, started 2013, and was the result of that competition was that we came up with 7 schemes, recommendations for usage, 7 schemes authenticating encryptions in a final portfolio in 3 categories. And I'm going to talk about this more in detail. With regard to lightweight authenticated encryption, now we have an ongoing competition which is run by NIST, and that competition has as a final goal the standardization of lightweight authenticated encryption standards. And at present, we are in the first round of that competition, and I'm going to come back to this in a minute or more. Back to the syntax of authenticated encryption, such that you don't forget what was it all about. As I said, take care with that thing called Nonce, and everything should be well. You have an authenticated encryption algorithm, taking these 3 inputs, returning these outputs, and a decrypt and verify algorithm that returns deterministically either the decryption or a symbol invalid if something went wrong. And as usual, the devil is in the details, and the devil is normally how you actually do the nonce. And as I said, that nonce has to be provisioned to be a unique value, a non-repeating value. It can be random value, but it doesn't have to be. So if you have a random value as the nonce, eventually you have collisions at the birthday bound. So if the nonce repeat, you might have problems. And the nonce repeats most probably and most commonly when we have the user mingling with the algorithm and trying to input the nonce in some way that is not regulated by that is not dictated by the algorithm. How the nonce is communicated is relevant to us. It can be communicated in band or out of band as long as the communicating parties know that they're using the same nonce. Everything should be okay. More formally about the security notion, maybe you don't want to hear about this, but just to give you a gist of how we reason about security of authenticated encryption schemes, we have the cryptographic community has kind of converged to the following security notion for authenticated encryption schemes. We say that we have some party called a distinguisher or an adversarial party that tries to distinguish between the real setting and some idealized setting of authenticated encryption. And in the real setting, we give access to that party to the real authenticated encryption box. And in the ideal setting, we say that there is going to be, he has black box access to some algorithms, to a box that returns random strings of the same length as here. So if he's good at telling apart these 2 worlds, then he breaks the confidentiality. And on the other hand, if he's good in telling apart these 2, then he breaks the authenticity of the message. And this is slightly more formally how we argue about security about the authenticated encryption setting. So with this notion in mind, how we approach security of an authenticated encryption scheme. So first, as Bart already mentioned, we have to be very clear of what we are aiming to achieve. So assume that this is what we were aiming to achieve, as I outlined in the previous slide. This is called, we want to satisfy that authenticated encryption security notion for some scheme. How do we go about proving that this scheme actually achieves that security? Well, most commonly, we rely on some assumptions on the basic building blocks. And what can these building blocks be? In this setting, most commonly we use either block ciphers, permutations, compression functions even, or a new type of primitive which we call fork cipher. And so there is some stated assumption on the security of these underlying primitives, and then if we assume that that security holds, and we can show that the scheme, that security is uplifted to the security of the overall scheme that uses these building blocks, then we have a security proof, and that security proof is usually built by contradiction. Namely, we assume that there is an adversary that breaks the scheme, then we can build another adversary that breaks the security of the underlying building block. And having this in mind, now I'm gonna just give you a snapshot of some provable authenticated encryption schemes prior to the NIST lightweight competition that you might have heard about. We have two standards, ISO standards, GCM and CCM. And GCM is the most used in TLS still. We have the OCB scheme, and these schemes basically belong to one of the categories. They are block cipher based, so their underlying primitive is a block cipher, and they are secure as long as the nonce is a unique value. But when you repeat the nonce, something happens here, their security breaks down very badly. So you might want to switch in such scenarios to this category. When you know you have applications where nonces might repeat, you go into this category of schemes. And these are schemes, here the blue schemes indicate submissions to the COSIC competition, and the red ones are finalists of this competition. And I have been involved in the column design, which is one of the finalists among these 7 COSIC candidates. And I'm going to come back to this one later. There is another category of schemes. These are the permutation-based designs, and they mostly follow the so-called sponge design methodology. I think yesterday you heard from Vincent about sponges, more in the context of hashing, but when you actually release part of the ciphertext on the way, and the final output is also the tag, then you actually can build authenticated encryption scheme from sponge-based constructions, given permutation as a building block. And Ascon is one of the finalists in the lightweight category here. However, these schemes again do fail when the nonce is repeated. If you want to use secure schemes when nonce are repeated and there's still some security left, then use these schemes. And I'm going to come back to the ape design that I have also been involved with. Now, what does this think about nonces? What happens when nonces repeat? I mentioned this, but you might not really understand what I'm referring to. So look at the designs. So you have just generic authenticated encryption, any nonce-based authenticated encryption scheme. It's very clear that if you have 2 identical messages and 2 distinct nonces, your ciphertext will differ. But if you repeat the nonces, your ciphertexts are identical. So you would leak information about the fact that you're encrypting identical messages for sure with nonce-based authenticated encryption schemes, and this fact is unavoidable. It happens for all nonce-based authenticated encryption schemes. However, some schemes fail even worse in the face of nonce repetitions. These popular designs, they actually have very bad forgeries, and they lose confidentiality immediately if nonces repeat. And this is not a theoretical result. This is a result that there are actually practical attacks coming out from this vulnerability of these schemes. We have had Unix attacks that have shown that there are some addresses that IP addresses that repeat the nonce, and then there is very trivial forgery attacks. There is the crack attack on wireless WPA technology that also breaks the security of the protocol. So this is only due to the fact that you can force the nonce to repeat, and only one nonce repetition is enough to actually break these protocols. And where do we have, when can we have nonce repetitions? Namely, if we don't take explicit care for that in our application, if we have a flawed implementation, or we leave that to the user to actually input the nonces himself, as I said earlier. But we don't want all security to be lost when nonces are repeated. So there is this second category of schemes that I showed that do resist nonce reuse, and they fall mostly into, there is two types of nonce misuse resistant schemes. One is that offers very strong protection, nothing leaks except the repetitions of messages. And another one is we allow for some small extra leakage. That is the longest common prefix of two messages. If they have the same prefix, that will be leaked, but nothing beyond that. So there is kind of some minimal form of distinguishing attack here. But if we allow for this, then and nothing else leaks from the computation, then we can build more efficient schemes. And these lists are such schemes. What is the COM design? The COM design is our design that reached the finalist, is a CSER finalist in the defense in depth category. What does it mean, defense in depth? It offers additional security, and here that means that we are secure against nonce misuse scenarios, which most of the other candidates were not. How do we achieve this? Well, maybe you don't have to really look into all the details here. We have some masking here going on. We have encryption, parallelized encryption, 2 layers of parallelized encryption, and this facilitates the implementation, more efficient implementation of that scheme. And this is a linear transformation in the middle. And this masking is incremented very efficiently also. And what is important to say that this is an online cipher, and the fact that it's online cipher allows for the nonce reuse security. And that means that every bit difference that you introduce in the message will be reflected immediately in the ciphertext. Only bit differences up to the level of processing will be reflected in the relevant ciphertext block, but not the next. So if you have identical prefixes, they are going to repeat, but once you introduce a difference, then that difference propagates into the ciphertext. That is the online property, and this is what is wanted for protection against nonce misuse resistance. Then we add authentication in the final part. This is the XOR sum of the messages, and that requires 2 extra encryption calls. And this encryption function here, for our purposes, is the AES function. The COM design also produces tags every few blocks, and this we call partial verification. So every few blocks we produce an intermediate tag, and that tag accumulates at the end. This is also a very nice property that helps us partially to avoid one other type of attack I haven't talked about. And that type of attack is what we came up in 2014. It's called release of unverified plaintext. What it means to have release, to be insecure against release of unverified plaintext, it means that there is this adversary that is able to read information before verification has been completed. So once the decryption algorithm starts working, it decrypts partially, but still maybe the algorithm needs to do the verification much later on. And in the meanwhile, the adversary is reading the information and maybe something is leaking about the actual algorithm and the key and so forth. And if that is possible for an adversary, and when would that be possible? If you actually have a small buffer, if you have a real-time requirement, if you have insecure memory, very constrained devices, some constrained environment, then you really have to release the data before it's verified. And if that happens, most of the authenticated encryption schemes fail. You have a valid attack. You have really bad security badly broken. Some people refer to this as a more physical type of attack, but if you have these requirements in place, then that is sure to happen. And while this was not part of conventional authenticated encryption security models, it has been recently incorporated in the defense in depth category. It has been explicitly put as a requirement. If you have protection against release of unverified plaintext, then you have a super secure scheme, super secure authenticated encryption scheme. And as you can see, these schemes do not have RUP, they don't have even Nonce reduced security. COM has Nonce reduced security, and this partial tag verification is a partial, not provable, but partial ad hoc protection against RUP from our side. And there is the 8 design, which is a permutation-based design, and these two pass very heavy designs that do offer security in both these settings. Just to give you an idea what is needed to go to do RUP security, to actually argue that RUP security, we can defend against RUP security, we have to view the authenticated encryption algorithm in a different way than what we have done so far. Namely, we need to split the decryption and verification box into 2 separate algorithms, the decryption algorithm and the verification algorithm. And while you might think that this is an artificial split, this is not the case, because almost all, I am not aware of any algorithm that doesn't have very clear separation between the decryption part and the verification part. Although we call it decrypt and verify algorithm, there is 2 separate subroutines that are done for each of these 2 functions. So once we split decryption explicit, that outputs message, and verification, then we can argue about RUP security. And RUP security is argued as RUP confidentiality and RUP authenticity. So we add to traditional indistinguishability notion plaintext awareness, and we redo a little bit the integrity notion to reflect that increased adversarial capabilities. This, you might not understand anything, maybe you don't look at it, listen to the explanation. This is to say that the plaintext awareness part that we add to the indistinguishability part says that basically an adversary shouldn't be learning more information from the decryption algorithm than what he's already learning from the encryption. The decryption doesn't leak information. And so this behavior is mimicked by this extractor here that mimics the decryption oracle and the decryption algorithm. And regarding integrity or authenticity, we wanted to capture such a behavior where the adversary reads decrypted messages and at some point is able to forge or not. And this is different. The difference between the previous scenario was that this box was 1 and the adversary never saw these decryptions. And in this case, in the RUP scenario, now he actually gets to see some valid decryptions. But as we said, if it's RUP secure, then this decryption shouldn't leak much information about what's going on. So in a way, you have to think about the decryption algorithm being some kind of behaving similarly to the encryption algorithm. Basically, it randomizes in some way the decryptions if they're not valid. And what is a scheme that is very easily secure and one-pass scheme secure against RUP? And I think it's one of the few. I'm not aware of many schemes secure against RUP. This is a very design that looks very much like sponge. If you remember from yesterday, there is this permutation. There is a capacity value here that is not output ever, and a rate part of the permutation that is propagated, and message is injected, and ciphertext is output from that value. So what happens here is that to achieve RUP, the fact that you have to look at the decryption. The decryption happens in the reverse direction. You need the inverse of the permutation. So in order to be successful in a forgery here, you have to produce the valid tag. Any wrong tag will give you a garbled output message under the assumption that the permutation is an ideal permutation, which is relatively strong assumption, but this is what we have at present to work with. And so this scheme is secure in the RUP model. It's secure against nonce misuse, nonce repetitions, and it's a lightweight design that proceeded up to the second round in the COSIC competition. I continue here with the public development efforts in this area, which have been a lot in the last, I would say, now here is 6, but more than 10 years. And we had the COSIC competition running from 2013 to 2019. And these are the 7 finalists in the competition. We had a category for high speed, a category for robustness, namely security, meaning security robustness here, and a lightweight category. And as COSIC was running, as you see, there was a light category here. The NIST came up with the idea that they need to, it's high time that they develop a dedicated or more understanding in lightweight authenticated encryption. So they started the NIST Lightweight Crypto project in 2015. 2017, they announced a report that was based on public comments and workshop gatherings together with specialists from industry and academia, and they said that they're launching in 2019 a competition for the standardization of lightweight authenticated encryption algorithms. And in March, there was the first round of candidates were announced, and these are 56 candidates in that round. What did they want in that competition? What were the requirements they listed that the submission should comply with? And these four entrances here indicate the requirements that should be satisfied by all candidates, namely authenticated encryption security as we defined it, security for unique nonces, and these are the minimum sizes for key, nonce, and this is the data limit, which is very prohibitive for lightweight applications. I must tell you that having a nonce of 96 bits and supporting a message of 2 to the 50 bytes is quite a lot when you think about lightweight. So this has pushed a little bit the candidates to propose somewhat heavy designs than they would want to, because they have to satisfy that limit set by the NIST requirements. But we had another exit from that situation. We were allowed, and everybody was allowed to give other candidates, to give a suite of candidates in their submission. So they have a primary recommendation together with secondary recommendations that most of the cases do not satisfy these last two requirements. They are for smaller nonces and for smaller data limits. This is the cryptanalytic resistance that the algorithm should satisfy to the 112 computation on a classical computer. The pluses, what are actually indicating the lightness of the algorithm. So this said that it would be great if your algorithm can be optimized either for short messages or for low area, power, for latency, or be performing wonderfully on various microcontroller architectures, should be efficient for pre-processing the key and so forth, side channel resistance, and most importantly, should perform much better than the AES GCM standard. And with that in mind, what happened is that 56 submissions came. This is the list. Please don't refer to it here. There is official website. I should possibly have put it here, but I forgot. 56 candidates. The following categories: block cipher-based, permutation-based, fork cipher-based, and stream cipher. Authenticated encryption schemes. More or less, the division between block cipher-based and permutation-based is 50-50, equal amounts in the both categories. And mode, what is the mode? Mode indicates that is this structure that we are building, like column structure, on top of the underlying primitive here, block cipher, to achieve authenticated encryption security. Here, this is most commonly counter mode, or OCB, or OFB. And here it's mostly based, the permutation-based designs mostly rely on the sponge methodology to encrypt and authenticate. So that category is new, and I'm going to talk about it now. Before that, first I want to give you a very motivational use case. This is the lightweight cryptography for very short messages. And that is not only a requirement by NIST, but also the eCrypt CSA report that I think Nigel also participated in says that the performance target for authenticated encryption, lightweight authenticated encryption design is wrong. Authenticated cipher is applied to many small messages, and the challenge here is to minimize overhead. What does it mean? Well, where are these applications? Everywhere. You can see applications for, when you think about lightweight application scenarios, most of the time you're dealing with very short messages. So 5G applications, automotive applications that already have their standard specified can go up to 4 128-bit data blocks. You have constrained narrow band IoT channels and so forth. So the domain space is very big. But how do we do this? Minimize cost for very short messages, as we read in the report. What does it mean to minimize cost? If we have an authenticated data and a message data, each of A and N blocks respectively, let's say that we want each block here to cost R1, where R1, for example, can be the number of rounds of the underlying primitive that we apply to process the authenticated data, and R2 can be the number of rounds of the building block that is used to process a message block. So we are aiming for something like that, where there is no constant overhead, there is no any additional term in that equation. And what happens with modes like the most popular, GCM, CCM, some other here from, this is the Caesar finalists, this is also from the Caesar competition, OCB, and so forth. What happens with these modes is that there is always at least one block cipher call, additional overhead, at least. Most of the time it's 2 or 3 or 4 per message block. Not per message block for the whole data, but there is this fixed constant overhead, which is very significant for small messages that we encounter, and that is because when you encrypt the data, you also need to authenticate it, and that requires one extra call to the building block. You can think about it that way. So how do we achieve something like A plus N building block calls for the shortest messages? This is a question we are asking ourselves, and if we try to look at the building blocks, so we are saying we need that many building blocks to process that long of a message in an authenticated encryption form. Take block cipher, take permutation, take compression function. What is the problem? Why can't we do that with these primitives? The problem is that none of these has integrity or a non-trivial redundancy check. So these will just encrypt, but there wouldn't be space for the authentication part. This is the same here, and this actually will compress the data. So a solution in that direction is the new primitive called fork cipher. And the fork cipher is the opposite of this function, but keyed. So you have a keyed expanding function that takes a message, a key, and a tweak. This is a public value. There is nothing secret about it. It's just used to randomize a bit the inputs. And then it outputs two values, C0 and C1. So it outputs double the length of the message. And we say that such a primitive, this is the forward direction of the operation of that primitive, is able to provide us, if this primitive is able to give us some form of authenticated encryption property, then for one single block of data, we'll be okay with just one application of this primitive. So there is not going to be any constant overhead as in the other modes. But for that, we need to design a mode such that it enables the processing of arbitrary length data. So this primitive here has various functions. It has the invertibility from C0 and C1. You can obtain M, of course, via the key and the tweak. And the same with the key and tweak, and C0 can go to C1. And the other one, direction, which we call the reconstruction property, which is slightly unusual property. Normally we don't deal with such properties in these three previous existing primitives. So taking a fork cipher, and we want to say something about it. In order to be able to work with this primitive, we want to assume or think about its security in some form and achieve some kind of security. And the security notion that we are aiming for is pseudo-random fork permutation. That means to say that the real instance is indistinguishable from what we will get as an output from two independent permutations. On the same tweak, for the same message, these two distinct permutations will give us ciphertexts that are not related in any way. So in this way, these two ciphertexts should not be related. And having this primitive in mind, we go on to build it. We have to actually construct that primitive because nobody so far has constructed such a primitive. And this primitive we construct based on the skinny cipher. It's a very well-known lightweight cipher. Also one of the submissions to the NIST competition. So the skinny cipher normally is just, let's say, the upper layer here, or the lower layer. You can think of it as any of these two layers is one skinny invocations. However, we use the same round function as skinny, the same tweak key schedule. However, the tweak key schedule for the lower part and the upper part, which we call the forking parts, are different, such that we break all the relationships between the outputs here. We also use different branch constant here. So the computation is identical until some, let's say, middle point. Middle point is a bit of an exaggeration. The computation is slightly less here and slightly stronger in this part. So we have more rounds in this in the forking points, which are of identical length. And so we start with the message key tweak. We update the key and the tweak. We use the round function of skinny. And then we output on this branch ciphertext 1 and here ciphertext 0 with different tweak key schedules. And we develop several variants of fork skinny, 64-bit variant and several 128-bit variants that vary depending on the tweak size. You can see that the tweak size, as it increases, the number of rounds also increases. And our primary recommendation was this variant in order to satisfy the security requirements set by NIST for nonce length and data limit, ability to process data of 2 to the 50 bytes. Now, we cannot do only with the fork cipher. The fork cipher is a building block. It only processes one block. So when we want to process various data, length data, so we go to the level of the mode. And what is the mode? There are several modes that we design, and for the associated data, it looks something like that, and this is for the parallel mode for the message part. What is interesting to notice here is that we don't need to use both branches of the fork cipher when we evaluate the associated data. Namely, we don't need to output the second part. For the associated data, let's say we need something lighter. As we said, there's also the security goal is different. We only need authenticity. So we output only the left part, and then we aggregate the output that is fed into a chain here with the message to produce later on the tag. And we use the full strength of the fork cipher to do the authenticated encryption part. So what emerges here is for a single block, you would just only do this thing. You output C0 and T, and you're done. For 2 blocks, you are going to have 2 invocations of the fork cipher. But what is the crux? Fork cipher does not equal 1 skinny invocation, or fork skinny is not equal to 1 skinny. So we have an overhead here, and that is 1 fork cipher evaluation or fork skinny evaluation is around 1.5 skinny evaluations. So we add a 0.5 overhead. Okay, that's very well. We can live with that because even then we are doing much better on short messages. But there is another mode that is actually representing, in essence, the problem of dealing with short messages. This is another parallel mode for which, in all blocks but the final block, we only output the left part. Namely, we use 1 skinny call, and the final part that outputs the tag, we use the full strength of the fork cipher. And that means for a single block, we still have this, but for 2 blocks, we only have 1 plus 1.5 skinny calls, 2.5 instead of 3 as before with the previous mode. So this is a very good property. So the challenge here is, for example, can you design something that is even better than that? Comes closer to the efficiency of skinny? Well, maybe you can. This table actually shows, thanks to Toon, our colleague here, he is the one who implemented our designs. These were paid designs, and SAFE is a sequential type of mode for fork skinny. And RPAVE was the last one I showed. So what this table shows, that if we take skinny best mode with 1 block overhead for the authenticated data, and this is the skinny cipher in the submission to the NIST competition. So we take the skinny submission, we compare with it for the respective block sizes and tweak sizes. We can see that a non-optimized implementation gives us a very good performance for small messages, which was our aim. We really have up to 40–50% improvement for small messages without an optimized implementation, round-based implementation. When we have a parallelized optimization, namely the 2 forks can be implemented in parallel, then we get better on all message sizes, and that ratio reduces asymptotically, but still for the very first 3, 4, 5 messages we vary between 10 and 50% of improvement. So the 10% is for the longer messages, which is very good. So this shows the cycles, the number of cycles for processing the message and the associated data. So this is my story, the one I wanted to tell you, and I want to give you some interesting topics that you might be interested to work on or to research. One message I always say is that security notions are not static, never stay static. They are all some dynamic mechanism, and they always evolve because our applications evolve. And so we always should question our security notions because our setup evolves. And the state-of-the-art in authenticated encryption has shown that this is the case here as well. Another topic that is actually very hot at the moment is the active analysis of the NIST lightweight candidates, both from cryptanalysis perspective, but also provable security analysis is really needed right now. And not only now, but in the next 4 or 5 years, that is where a lot of effort is going to go into. Another topic is what is the role of authenticated encryption for data and computation, or what if you want to use authenticated encryption for the purposes that Nigel is going to talk about. And maybe Nigel is going to tell you how you can do that. He's not going to tell you, and you have to research yourself on that. But there is hardly any answers here. We don't know much. And then design principle for short messages. Maybe there are others. New fork cipher paradigms. It's a very new topic. A lot of questions rise here, so if you want to work on that topic, I'll be glad to. I myself will work a lot here. What is a side channel security, a ForkAE, and so forth. There is many more questions, but these are some of them, the ones I wanted to present to you. And with that, I conclude my talk, and thank you for your time.